Let's explore one of the most profound and perplexing problems in computer science and mathematics: P versus NP. This problem is not just an academic curiosity. It carries a $1 million prize and could revolutionize fields from cryptography to optimization. Welcome to the journey of understanding P versus NP, the Millennium Problem. First, let's define what we mean by P. P stands for polynomial time. These are problems that a deterministic Turing machine, a theoretical model of a computer, can solve in polynomial time. Essentially, the time it takes to solve the problem grows at most polynomially with the size of the input, denoted as n to the power of k, where k is some constant. This means that as the size of the problem increases, the solving time increases reasonably, making these problems efficiently solvable. Now, consider some examples of problems that fall into the P category. One classic example is sorting. Efficient algorithms like merge sort or quicksort can sort a list of items in O of n log n time, which is polynomial. Another example is finding the shortest path in a graph, which can be solved using algorithms like Dijkstra's in O of v squared time, where v represents the number of vertices in the graph. These problems can be solved quickly by a computer. Next, we have NP, which stands for Nondeterministic Polynomial Time. These are problems for which, if given a potential solution, that solution can be verified in polynomial time. In other words, while finding a solution might be hard, checking whether a given solution is correct is easy. As the saying goes, these are problems that are easy to check but hard to solve. Examples of NP problems include the 3 SAT problem, which deals with the satisfiability of Boolean formulas, and the traveling salesman problem, or TSP, which seeks the shortest possible route that visits each city exactly once and returns to the starting city. While finding the optimal solution to these problems can be computationally intensive, verifying a proposed solution is relatively quick. So here's the central question: does P equal NP? In other words, if a solution to a problem can be verified quickly, can the problem also be solved quickly? If P equals NP, it would mean that every problem whose solution can be quickly verified can also be quickly solved. This would have enormous implications for various fields, but it remains one of the greatest unsolved problems in computer science. The implications of solving P versus NP are vast. For instance, in cryptography, many encryption methods rely on the assumption that certain problems are hard to solve. If P equals NP, these methods could be broken, revolutionizing data security. Similarly, in optimization, finding the most efficient way to allocate resources is often an NP problem. If P equals NP, we could efficiently solve many optimization problems, leading to better resource allocation and efficiency gains. As of now, the P versus NP problem remains unsolved. It is one of the 7 Millennium Prize problems selected by the Clay Mathematics Institute, with a $1 million reward for the first correct solution. The quest to solve this problem continues to drive research and innovation in computer science and mathematics, as scientists and researchers around the world seek to unravel its mysteries. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.